Hi everyone. So in this video we will see one more way of studying or deriving the expression for radial acceleration. Okay. Now I'm discussing two ways just to strengthen the concept of this circular motion. Okay. Acha. Now we have this particle which is moving in a circular path. Okay. It is moving like this in anti-clockwise direction. So at location A and B, we are marking the direction of velocity. Okay, that is done by drawing a tangent. So at A, this is the tangent. So this is the direction of velocity. At A, it is marked as V1. At B, again, one tangent is drawn, and this is the direction of velocity V2 at B. Okay, Acha. Now let's say this angle is theta. So when the particle goes from A to B, the radius vector, okay, so this is the radius vector. Now this radius vector turns through an angle theta. Radius vector turns through an angle theta. Okay. Acha. Now let us shift the vectors v1 and v2. Okay. So see v2, it is in this direction. So this is vector v2. Okay. And this is vector v1. Okay. Now if the particle goes from A to B and the radius vector turns through angle theta, that means v2 turns through an angle theta with respect to v1. Okay. So that means this angle is theta. This angle is theta. Okay. Acha. Now see, if v1 is in the upward direction, so what will be minus v1? It will be in the opposite direction. So this is minus v1. Minus v1. Okay. Acha. So the resultant of v2 and minus v1, it will be in this direction. Okay. So this is the resultant of v2 and minus v1. So this is delta v, where delta v is equal to v2 minus v1. v2 minus v1, or we can write this as v2 or we can write this as v2 plus minus v1. That means we are taking the resultant of v2 and minus v1. Okay, so this is the resultant. So this is delta v. This is delta v. Okay, theta is the angle between v1 and v2. So this angle, the angle between v2 and minus v1, this angle, this total angle will be pi minus theta. Pi minus theta. Okay. Acha. Now what about the magnitude of this delta v? So magnitude of this delta v magnitude, it will be equal to square root of v2 square plus v1 square plus twice v1 v2 cos, angle is pi minus theta, so cos pi minus theta. Okay, this is the magnitude. Magnitude of delta v means magnitude of change in velocity. Okay, so delta v means, this means magnitude of change in velocity. Change in velocity. Okay. Acha. Now, if the particle is moving with uniform circular motion, then it implies magnitude of v1, it is equal to magnitude of v2 is equal to v. So here this v2 square, v1 square, all these things can be replaced by v square. Okay. So we have a delta v is equal to square root of v square plus v square plus 2v square. Now cos pi minus theta, it is minus cos theta. Minus cos theta. Okay. So this is equal to twice v square minus twice v square cos theta, square root of this. Okay. So this is twice v square 1 minus cos theta square root of this. Okay, 1 minus cos theta is 2 sin square theta by 2. So twice v square into 2 sin square theta by 2 square root of this. So that gives delta v is equal to twice v sin theta by 2. Okay. Achha. Now see here if r is the radius and the particle goes from A to B in time delta t. Okay. So here I can write, see, A to B the arc length. A to B the arc length is r into theta. Arc length will be r into theta. Okay. So that will be equal to, if v is the speed, v times delta t. Okay. V times delta t. Okay. Achha. Now what is the net acceleration? What is the net acceleration here? See, net acceleration, A net, magnitude of net acceleration, it will be delta v, magnitude of delta v by delta t. Okay. And what is delta v? Delta v is twice v sine theta by 2 divided by delta t. Okay. Delta t, from this I can write r theta by v, r theta by v. Okay. Now if we assume this angle to be small, okay, if this angle is small, this angle is small, so in that case this sine theta can be replaced by theta. For small angle, sine theta is approximately equal to theta. Okay, so sine theta is equal to theta. So this sine theta by 2 becomes theta by 2. So this is 2v theta by 2 r theta by v. Okay, so here what all terms can be cancelled? See, this 2 and this 2 gets cancelled. This theta gets cancelled. V goes to the numerator. So this is equal to v square by r. V square by r. So what is this? This is the net acceleration. Okay, so we have the expression for net acceleration. So we have A net, it is equal to v square by r. V square by r. Okay. Now again, see, circular motion, we have two accelerations. One is tangential acceleration, the other one is radial acceleration. Okay. This is radial acceleration. Okay. Now AR, this is AR, this is AT, tangential acceleration. Now uniform circular motion means AT is equal to 0. So that means the net acceleration will be along the radial direction. So that means this is the expression for radial acceleration. Radial acceleration. Okay. Achha. Now let's see what is the direction. Why we are saying that it is acting along the radial direction. See, we had this as velocity VA. This is VB. And this is delta V. Okay, this is delta V. Now and this is theta. Okay. Now for small theta, this delta V will be perpendicular to VA. Okay. For small theta, that means theta tends to 0. Delta V is perpendicular to VA. Delta V is perpendicular to VA. Okay. Now VA is tangential to the radius. Okay, VA is tangential to the radius. That means if particle is moving like this, so VA is in this direction, VA is tangential to the radius. Delta V is perpendicular to VA, so that means delta V will be in this direction, perpendicular to the this VA. So this is the direction of delta V. This is the direction of delta V. Okay. Delta V is along the radial direction, it implies. Now since delta V is along, now what is A net? See, A net is delta V by delta t. A net is delta V by delta t. Now delta V is along the radial direction. So that means net acceleration will be in the radial direction, provided it is uniform circular motion. Uniform circular motion. Why uniform circular motion? Only because only in uniform circular motion the tangential acceleration is 0, and that means we are talking about acceleration along the radial direction. Okay, so hence we can say that it is the radial acceleration, it is acting along the radial direction.